I guess we can, I think we can just roll here if y'all are ready.
Yeah.
Everyone shows up, they'll catch up, or they can stop me. So I guess I'll toss it up there. Today we're gonna do ordinary differential equations, which I'm noting because later I think we're gonna do partial differential equations, which are special and unordinary. But yeah, as I mentioned, let me know if I'm going too slow or too fast. I planned on starting at like the very basics, but if it's too basic, we can just skip ahead to the next part. Yeah, as I was like thinking about what this was going to be about, I realized basically crash course calculus with some added application is really what's going on here. But okay, so the reason there's differences in differential equations is ordinary differential equations are just looking at the change in one variable with relation to another. So different types of differential equations might look at different variables. Sorry, I'm going to switch this because last time we recorded it and people joined and it made it really tiny and even harder to see. I didn't either. I just went to post it. How do I make myself big? Okay, there we go. Yeah. So ODEs are only one independent variable. Derivatives are only with respect to that variable and another, but we'll kind of circle back to that in a second. So as the name suggests, they're differential, which means we're going to be taking derivatives. And I figured we'd start with like, what is a derivative conceptually and how this is going to tie into differential equations. So this is the part that might be a little slow and we can like just kind of skip through. So we all know how to calculate slope of something. So if I just had a line, or this is 1 and this is 1, and this is the point 1, 1. We know, I mean, we all know that the slope of this is 1, but the process we go through of calculating that slope is very similar to the process conceptually what's going behind the scenes as derivatives. So, you know, it's x2 minus x1, where this is x2 and this is x1 over, oh, I got that backwards. It's y2 minus y1 over x2 minus x1. And basically what that turns into is y is just a function of x, right? So if I have any x value, I can figure out the corresponding y value. So this is just f of x2 minus f of x1 over x2 minus x1. And so even though this seems really trivial, we'll keep that in mind that importantly, y is a function of x and the derivative is just going to be the change in one variable over the change in the other. Okay, so we've got our straight line, but now what if our line is not straight? So now we've got, what if we have a curve?
Wait, can you repeat the like the fx2
Yeah, so this line is the line y equals x, right? 1 equals 1. So y is just a function of x. So if I know any x value, I can figure out the y value based on that x value. So if x is 1, I know y is 1. So I really don't need to keep track of y separately. It's just a function of x, if that makes sense. So what if I have something that's curved? This is, we'll just say this is y equals x squared now. Well, certainly by the same logic, I could take the slope between point, 0 and point 1, 1, and the slope of this line would be 1. But that's not really representative of the whole slope, because if I took the slope between 1 and 2, and now this is 4, not to scale, the slope of this line is going to be different than the slope of this line. I think it's what? 3 instead. So the reason we have differential equations is to kind of encapsulate this issue. So if I wanted to find just the slope at 0.11, I can't really do that because that line, we're blind to everything around that point, right? So if I wanted to say y equals x squared, what's the slope at exactly 1? I don't know if that line's doing this or this or this because there's no other reference point around it. And so if I wanted to know how the slope changes over this whole thing at any given point, I couldn't figure that out with just this method of saying, okay, pick 2 random points, calculate the line. But what I can do is say, what if I want to find the slope between 1 and like 1.0000001. And now I've made just a little tiny change. So it's not precise, but I'm still like basically at 1. And so that's kind of what the derivative does. So I'll write out like the math definition and then we'll go back through it. So if I want to find the derivative at any given point, it's the limit as that change in x along this axis goes to 0 of this function of x plus that change in x. So this is just our change in y again, by the same logic that it's just our change in y up here, over that change in x. So with limits, we're never actually going to get to 0. Like delta x is never going to equal 0. We're just going to make it tinier and tinier and tinier and tinier and tinier to where to us it doesn't matter because it's so close, it's basically there. And so we're going to look at that point here. We're going to move a little itty bitty bit over. We'll calculate the value at that point here. Oh, this is a mess now, and then we'll calculate the slope between those points. And we'll do that for every single point along that curve. So we'll plug it in. So y equals f of x, y equals x squared, so f of x is equal to x squared. So that one will calculate f of x plus delta x. And all we have to do is plug in x plus delta x for x. And I'm not going to work out the algebra unless you really want me to, but it works out to x squared plus 2x plus delta x squared. I just boiled it out. So now we know f of x plus delta x, we know f of x, and we know what delta x is. And we can plug all those values in. So we can say this is x squared plus 2x plus delta x minus x squared f of x. Oh, I have a mistake. Yeah, we're missing a delta x. 2x delta x all over delta x. So, and it's still a limit. So these guys are going to cancel. We're left with 2x plus 1. I have some sort of error here. Oh, no, I don't. I'm good. I do have an error. It's this. Sorry. I was like, this shouldn't have a 1 in it when we're done. I'll rewrite it more clear. So it's 2x delta x plus squared. Which leaves us with all over delta x, and we'll just cancel these guys. So this guy cancels with that guy. We're trashing one of those. And then in the end, the big takeaway is that you get the limit as delta x goes to 0 of 2x plus delta x. So even though that doesn't seem like we've solved it, because this limit is getting so close to 0, it's basically equal to 0. Like it's so close, we just don't care. We say that this is just 2x, and that's it. And so that works out really nicely visually too. So if we draw another nice curve here where y is equal to x squared. Here's 1, 1. Here's 2. Now, instead of actually calculating the slope between these points, I've got this great function that the change in y over the change in x is just 2x. So if I say, okay, x is 1, the slope of here is 2. I said, okay, x is 2, the slope of here, 4. And I can do that for any point on this line. So now rather than having to calculate these weird tangent lines, even though that's kind of what this is doing, we have this continuous curve that represents how x is changing with respect to another variable, or how y changes with respect to x. Okay. So the cool thing about derivatives is, much like the graph itself, you can plot those. So if this is my derivative, and this is x, we know that it is just, is this a mistake? I was like, something is backwards. And it's just the line with slope 2. And we'll circle back with a much more worked through example on that. Okay, so what if we have a curve that's not just some trivial y equals x squared, or y equals x, it's some system that we actually care about. So let's say that I have a population of n individuals over here that are going to change in time. So we've got n things changing with respect to time t. And so this does something like this, to where we've got a curve, and maybe our population starts growing and then eventually dies. And so we know that, and we just know this, we're just going to take that we know the equation for our system, and we know that n of t is equal to, we know that this is the equation for this curve. So that's great, we've got an equation for a curve, but maybe it would interest us to know when our population is growing, when it is declining, when it's going to stay constant. Because I can kind of look at this and say, okay, we're growing to here, we're declining to here, but like, what time is that? Can I just eyeball my graph and say, I don't know, this looks like, if this is like 10, this is 4, I don't know. So if we actually take the derivative of this, we can find out when we're growing, staying the same, and declining. So essentially, we're going to use the same process, and I'm not going to get too into it, we're not going to do that big limit derivation of derivatives. There's shorthand rules. If you ever feel so compelled to calculate your derivatives by hand, there's tricks that make it much faster, but we're just going to pretend that we plugged it into the computer and it gave us the answer. So we know that n changes with respect to t, and it's just -2 t minus 2. And so the trick is that after we solve for our derivative, we can answer questions like that. So because we know the change in n, the change in t, so what if I said, okay, when is there no change? So 0 is equal to dn dt, which is equal to -2 minus 2 is equal to 0. And we can just solve, and we can see that, at t equals exactly 2, we're not changing at all. So now I can go back into my original graph, and I know that at t2, the slope of this derivative is 0. And so we're going to remember that derivative is just the slope of the tangent line at a given point. So And we can also find the value of n at that point as well. So we know what time and what population size our system is constant at. So we can just say, okay, we started with our original equation. We know t equals 2, the population is unchanging. So we can say n of 2 is negative, 2 minus 2 squared plus 10. So it's equal to 10. So we know that at 2, 10, if we stayed exactly at that point, nothing would happen. And by the same extended logic, we can also find, where dn dt is less than 0, so our population is shrinking. dn dt is greater than 0, so our population is growing. And you can plot that out visually as well. So are we all together? Great. Okay, so
So this mostly is part of a logical, like in a logical context, we can apply that language context to. Yes.
I mean, like, yes, you can apply it to anything. So any system where one thing changes with respect to another can be represented this way. So, speed of a car, change in space over change in time, right? Classic example.
Fitness gradients.
Change in fitness over change in environmental variation. Symbiotic concentration. I could do, if I had a coral that had, lots of symbionts over here, and then less, and then less, and then less, I could say, okay, what's change in symbiont over change in coral space? And I would have some equation that I think represents that system. So, maybe there are twice as many over here, or this many squared over here, or et cetera. But because it's not constant in space, I probably want to represent that somehow. And that's what I'm doing with my model, by the way. That's like the core, what's going on is things are changing with respect to other things. So the cool thing, once you have your derivative, especially once I think Nikun is going to do 2D, 3D systems of this next week, is you can represent that also in graphical space. So this is our t, this is our dn, dt. We know our derivative is equal to negative 2t minus 2, which is also the same as negative 2t plus 4. I can say, okay, we've got 1 point at 4. We know it's 0 at 2. These are really not to scale. Just bear with me. And so our derivative looks like this. So as t changes, this is now the value of our dn dt. And we get that from our equation. So what's cool about thinking about it this way is anytime this line crosses the axis, there's no change in your system. Anytime this line is above the x-axis, your system is growing. Anytime it's below, your system is declining. So this is the same as saying dn dt is greater than 0, dn dt is less than 0. And when you think about the potential stability of these points, it's just, you can do this like nifty little thing graphically, where if it's greater than 0, you draw a right-hand arrow. If it's less than 0, you draw a left-hand arrow. And it shows you that we're going to kind of come into that point. Which is kind of trivial in this case, where it's just a line, but you can imagine that if I had, let's do something like this.
Carly, what's the x-axis?
Oh, it's t. It's a change in population size in t, unless, I think I'm pretty sure that's right.
Shouldn't it be n?
No, because n dn dt is.
Because time can, so those arrows don't make sense. If it's t, then you're saying that you're moving towards some equilibrium time.
Oh, you're right.
That's not what you're doing.
I see what you're saying.
The time is like a third axis. Here, like this dn by dt and population on the x-axis.
So it should be n on the x, oh, yeah, it should be. And then this is actually 10,
Yep.
if you want. Sorry, real quick math check. Do I have this flipped maybe? D and dt. No,
If we were to integrate it,
it would be
back to
right,
t,
yeah.
you would get n back. So that is d and dt. Well, let's just.
At the end, it looks,
Because that's definitely the right solution. Lots more points. We could say, okay.
You've drawn now is fine.
Huh?
I'm saying is the graph is the only thing that was a bit like the x-axis
Oh.
didn't make sense. But now, like if you put n on the x-axis, that should be fine, because then what you can say is that let's start from something at time t equals to 0. Let's start something less than this is the place where that it intersects the x-axis. And then as the time increases, because dn by dt is positive, n will increase. And so you can draw an arrow pointing towards the intercept. Yes.
but I think you have something wrong with the graph.
I do have something wrong with the graphs.
It's like you should have your x-intercept should be related to on the y-axis. Your y-intercept.
We can also just circle back. I'm gonna be honest, I haven't done this in 1D in so long, I'm not entirely sure.
I'm sure where the.
Right,
Like
because-
n and n to what? It's the output of t, so I guess just pick 110 t.
Yeah, I don't think,
We would get, let's just pick like 0.
yeah,
We
let's-
would get out 10 in n,
right.
and then what would we get out in dn dt? If we plugged in 0, we would
We
get
get
out
out
0, which is,
That's right.
so, well, it'd be actually the or like, yeah. In 10 out 0, so that one would be correct, that's why
That's
it's
right.
10.
That's would be 10 and n,
Uh-huh.
but it would be
Nine,
more-
0, so now let's just pick,
let's pick, okay, what if t is 3? So it would be 3 minus 2, which is 1, so it would be 9, so n,
that one. So what's dn? That's 2 plugged in
3, it would be 3 minus 2, so negative 2,
-2.
which makes,
It's, I guess the line's going to be off in the direction.
is it going the opposite direction?
Well, I'm just saying, like, if we plug in
Right,
9, we get out -2, so that one's good.
right,
Right,
so
and now
that
go back
it's
one.
negative 2. So then add t equals, let's say 4, minus 2 is 2 squared, so it would be 6.
Looks like it's time to increasing or decay, which is true,
Which
based
is
on our
based on our first,
arc.
yeah.
So as time increases, we decay. You know, they're a stable point, and if 10's our stable point, then any bigger t's, we're gonna go down.
Right. So t is greater than 2, and goes down. At t is less than 2, and goes up. Which is why I have this with t.
Yeah, I feel like it was okay as a function of t. Like, obviously, there's nothing wrong with either graph. But whether or not one is the base.
Yeah, I don't think it's phase.
It's a base function of t. It's easy.
Well, how about we just say that you can obviously see that if t is less than 2, we go up. If t is greater than 2, we go down. If t is exactly 2, we stay in the same place, and we will circle back maybe on how to do this in 1 dimension, either after we get through or in 2 weeks.
You did great.
Yeah, we'll just call it there. we'll forget about your t versus n. That would definitely be, well, yeah, that definitely was the graph of our derivative, whether or not you can make some claim about stability where it crosses zero. I think we're unsure. Okay. I lost my train of thought. Okay, so I think this is less than an hour's worth of stuff, which is fine. So I guess the big question is now we actually have a differential equation, which is dn dt is equal to -2 t minus 2. So it's a differential equation because of this. But let's say we didn't know that we started with n of t is -t minus 2 squared plus 10. What if we only knew how our system changed in time? So erase these for now. Yeah, so we're going to pretend we don't know this. But we do know this. So much in the same way we can go from a regular equation to a differential equation, we can go from a differential equation back to a regular solution. And so in these cases, there's many different forms of differential equations. This one's the easiest. If it doesn't look really easy, just put it into R and solve it. Don't try to, you can do them analytically by hand, but they get increasingly more complicated. The more complicated this right-hand side of the equation is. So what makes this form so special is it's called separable. So we can rewrite this as dn dt is equal to -2t plus 4. And so my goal in a separable equation is to have all of the n's on one side and all of the t's on the other side. So I can say this is dn is equal to -2t plus 4 dt. So all my n's are over here, all of my t's are over here. Depending on the form of this equation, you can't always do this, but in these cases you can, and that's like the gold standard of like analytically solving differential equations. And so the reason that's so important is because now we can just integrate both sides. So all integrals are is the opposite of a derivative. In this context, they have other meanings. But in this context, all we're going to use integration to do is to get rid of the d's in our derivatives. So the integral of dn is just n, and I don't think we're going to go through how to actually do this. Just take my word for it. Or at this point, we can just look it up, put it in a graphing calculator. And then on this side, you end up with so we scratched our t's, our dt, and we integrate this, it returns this. So now we have n equals this function. But the catch with integrals is because we don't know where we started, there's this arbitrary constant that's added to it. So you can imagine that, sorry, I should have written this in extended form as well. This is what t sorry, this is this written out. So you can see that we totally got this part just from our integral, right? So we integrated, we got back out this part that's relative to t, but we lost this plus 10 by doing this. So what we can do if we know one of the initial conditions of our problem is we can go back and solve for that c. So you know that at, let's say, if t is equal to 0, n is equal to 6. And so we can plug that point in down here if we know it. So we might know where we start, but not the whole equation. So say I have a population at a given time. I probably know how many individuals are in that population at this time.
That needs to be plus 6 at the bottom of that.
This,
Of the extendable that you just did above on the top.
this,
You forgot the minus, you forgot to do a 4.
let's, yeah, okay, yeah, that's right. Yeah, that's right. We still got this, we didn't get the +6, but we're about to get that back just by plugging in here. So we can say 6 is equal to 0 plus 0 plus c, super easy. We know c is 6. And now we have our full equation back being +14 plus 6. So we can totally get it back with just one initial condition, which is great. Because again, we usually know that. So the question for me, and when I took differential equations, is why in the world do so many things have exponential growth or exponential decay in them? Because it's great to see like this, okay, we get back this nice quadratic equation, everything's really neat. And long story short, at least mathematically, it's an artifact of just the kind of the way integrals work. So let's say I'm going to do a harder but still separable equation. So let's say I've got my change in y over my change in x is equal to something like this. So even though we have two variables on the right-hand side, this equation is still separable because we can say, okay, that's equal to y times x squared plus 1. And now we can just say, we can bring this guy over on the other side. So we've just rearranged things algebraically from here to here. We haven't done any calculus, just moved things around. And now you can see again, all the y's are on the same side, all of the x's are on the same side, which is great because we can integrate both sides. So this side, easy math rules again. It's just 1/3 x cubed plus x. But on this side, you get this integral of 1 over y. And whenever you have the integral of 1 over your variable, it actually comes back to be the natural log of that variable. And so if we want to know what y equals in this equation, the only way to get rid of this natural log is to raise it to the e power. So then you get e to the 1/3 x cubed plus x plus some arbitrary constant. And so this comes out again and again and again to where if your y is in the numerator on the right-hand side of your equation, you're probably going to get an exponential form back when you solve it. And so that's why when we do like logistic growth, well, not logistic growth, sorry, exponential growth, even though the differential equation looks linear, your solution is exponential. I don't know if anyone has any questions on that, but it's just a fun integral fact. And that's sort of where I had thought about leaving off, unless you all want to go through the exercise of building a really simple differential equation from some hypothetical system. Which would be cool. So like, we know how to solve them. We know what they look like. What if I wanted to just write one?
Or could you go over really quickly, like, just how to like, why identify the differential equation, like what, that just looks kind of like a derivative one. Or is it differential?
I mean, differential equation is just basically an equation containing a derivative. Yeah, that's what the differential and derivative, basically the same thing.
Okay.
Yeah.
It's usually like something time dependent.
Yeah.
Whereas like a lot of like other algebra we do is like a single point, right?
Mhm.
If there's no function of, these are functions of t. So like n is a function of t, and then we're going to take the derivative of that. So we're not just taking the derivative of something that's time independent,
Yeah.
right?
Like, or it could change in space as well as do like the coral if I change it over the surface of the coral. We'll get to it if we do partial differential equations. Things can change in time and space, as we all know. And so basically, differential equations are anything that changes with respect to something else.
A lot of times, especially with regard to change over time, they're also called dynamic models.
Mhm.
Dynamic models being the differential.
Yeah, dynamic models almost always mean it's a differential equation or something similar.
But I think dynamic just means changing in
Yeah,
time.
so there can also be discrete versions of it.
Yeah, I mean, a lot of times these things end up,
It's like
Just read-
continuous time versus
yeah.
like, because, yeah, your computer doesn't need to do continuous time, if you can just do like a discrete approximation.
your computer doesn't, yeah. Honestly, your computer can never handle a continuous equation. It just breaks it like we did with the derivative into tinier and tinier and tinier chunks until it looks continuous. But obviously, your computer must operate in finite little chunks. And sometimes that leads to wild computation errors if you make those chunks too tiny. Yeah, so if you want to go through, we'll go through a super easy building of a differential equation. And I think that will be where we leave off. I don't think we'll solve it or anything. Okay, so what if, these are great boxes. Okay, what if I have some population of people who are infected with the disease? Okay, those people who are infected with the disease can become recovered. So we know that these people can become these people. I will say this time that you can get this disease over and over and over again. It's really bad. It's like a common cold. So you know that your infected people become recovered, huh? I wasn't going to do the S. I was going to keep it simple.
Oh. SIS, they can always become
Oh, you
susceptible
mean-
again,
Yeah,
so that's usually how, or just. like-
yeah. I was going to leave. I guess I can put the S in.
No,
It
I'm,
could be an S and the R.
I was
Yeah,
just
so-
saying like R usually is like.
Oh,
end
they
of the
can
row
remember,
versus
yeah, okay.
S, you change that,
You're right,
it
you're
means
right,
you can
yeah.
always go back and forth. Yeah, like.
Yeah. We can always go back and forth. I see what you're saying. I'm like, oh, I was going to leave out the S because that would be 3 and we're just going to stop at 2.
No, just.
Yeah, so your infected people become susceptible, again, when they're not actively sick, at some infection rate, or sorry, some recovery rate. Those susceptible people become infected, unfortunately, at some other rate that you've decided from your data, or you've just like arbitrarily picked something that's reasonable. And let's say, because we all live in the world, these guys can die at some death rate. And these guys can die at some other but lower death rate. So you can always die, we're all human. You have a lot higher rate of dying here than you do over here. And so let's say I'm interested in how these populations are changing in time. So, you know, what do my eyes look like over time? What do my S's look like over time? And what can I learn about that system, you know, by modeling it out? So I'm interested in the change in my eyes over the change in time. And I'm also interested in the change in my S's over the change in time. And so when you have these plots, any arrows going out of the box are losing individuals, any arrows coming into a box, you're gaining individuals. So when I'm thinking about the change in I, I'm losing some R of my individuals, they're becoming recovered. I'm gaining whoever's getting infected from S. And then I'm also losing people who are just dying into the abyss. And then I can do the same thing for my S equation. So I can say, okay, I'm losing these I's. I'm gaining these recoveries. And I'm losing people, maybe not into the abyss, but just due to natural causes, car accidents, whatever. And so just like that, with anything that you can draw out in boxes with arrows, yeah,
Maybe minus.
yes. Yeah, no, they're coming back from the dead, Christopher. Yeah, I'm gaining people who are zombies back from death, but yeah, anything that you can draw out in boxes, you can then just represent in forms like this. And I don't think we'll get into it today, but you can do all sorts of things once you have things in a system like this. So you can say, you know, how does I change dependent on S? Or for real, where is the system stable or unstable? What happens if I perturb a seemingly stable system just a little bit? And that's what we talked about that a lot in Tim's class, and that's where that's coming from. So you have all these populations that exist with relationships to each other. And those differential equations are just a way of measuring how those relationships change in time. So, yeah, that's all I had. Does anyone have questions on this?